welcome you to this lecture on marine hydrodynamics. In the last couple of lectures we have already talked about small amplitude wave theory, and then we have considered few special cases, few phenomena associated with this certain physical calculation of or computation of certain physical quantities like the energy, pressure, how we calculate associated with a wave, that is when it is propagating. Basically our concern is the wave propagation in a water. Now as we have seen that in the always we define or we model any physical model we develop, always certain assumptions are required. For ease of computation, and so we always idealize the problems, and also in the process of idealization many times the problems are simplified, and this idealization varies from case to case. Like when we are dealing with highly nonlinear waves in the ocean, and if you look at the calculation of the wave forces on cylinders on particularly large substructures, then in fact our linearization small amplitude wave theory sometimes may not hold good. In such situation, what we do, we always look into the finite amplitude wave theory and consider, that is basically we talk about the Stokes finite amplitude wave theory, and then you consider first order, second order, third order and higher order wave theories. Of course, this individual order of the theory, they are also a generalization, another case of idealization from the general nonlinear wave equations and the boundary conditions. In the same manner, suppose we are looking into problems related to storm, tide, tsunami, then we have a different kind of a situation there altogether, and these are all kinds of in many situations we analyze them as long waves, and for the very basic reason of analysis, again we linearize it with certain approximation and parameterization. So this in today's lecture, what we will do, we will talk about the linearized long wave equations, particularly where we have seen that out of the three types of wave, deep water waves, shallow water waves and finite intermediate waves of intermediate depth, we have seen the small amplitude shallow water refers to the case that where C is root G h, and in that case h by lambda is less than 1 by 20. So in fact, in the past people have developed theory where directly we can get that a wave equation, particularly we satisfy the wave, it satisfies the wave equation with C is root G h. So let us see today how the long wave theory is evolved, particularly under the assumption of the small amplitude wave theory. So with this background, let us start to have a look at the Euler equation of motion. We have the firstly I will consider that as if I am calling with a two dimensional, I will consider two dimensional problem, two dimensional, and then I will have in two dimensional, suppose since I say water is a fluid, assuming water is fluid is inviscid, and incompressible. Fluid is inviscid and incompressible. We have the continuity equation del v by del x plus del v by del y 0. This is comes from the continuity equation, and we have the Euler equation of motion, that is the equation of continuity. And we have equation of motion, and the component wise they are nothing but del v by del t So, since I am considering there are two dimensional equation, this is the x coordinate, x component, and this is the y component of the equation of motion. Then we assume in the case of the derivation of the small amplitude long wave theory, we assume that v is negligible, vertical velocity v is negligible. That means the vertical velocity of the water particle is assumed to be negligible. So, if v is negligible, then what will happen to from equation 2, this I call it b, this I call it as a. From b what will we get? We will see the left side is all terms will be 0, and that will give us 1 by rho del p by del x plus j is equal to 0, which implies p is equal to minus rho g y plus f of x t, where f of x t is an arbitrary function of f, because derivative is independent of x, so it has to be a function of x and t. Sorry, and this is del p by, I am sorry, this is y, this is y. So, in the process what will happen, and on the free surface on y is equal to eta, that is on the free surface p is equal to p atmosphere, and this is our assumption. So, if p atmosphere is assumed, the p atmosphere is constant, which can be taken without loss of generality, p atmosphere can be taken as 0, as we have done in case of small amplitude wave theory. So, in that process what happened, that gives me from this assumption we get f of x t will be rho g eta, which implies p is equal to minus rho g y plus rho g eta. This is the hydrodynamic pressure, this is the pressure, and that we are getting from equation b. Now, if we substitute for this in the first equation, this is c. If I substitute for c in A, then what we get, and again consider only the linear terms. So, we have got del u by del t, because second term will contribute to 0, third term is a term v is involved, so v is negligible, and on the right side minus 1 by rho. So, that will give me minus 1 by rho del by del x, p is minus rho g y plus rho g eta, and that gives me minus g into del eta by del x. So, that gives me del u by del t minus g into del eta by del x. So, in the process, so this is the linearized long wave equation of motion. Now, again if we will go back, what I say that we have from here, another thing we will see that this is what it says, that the eta is a function of x and t. If eta is a function of x and t, so del u by del t, this right side is a function of x and t. So, that means del u by del t is a function of x and t. So, I can say u is equal to u x t. That means the horizontal component of velocity is only depending on the x and t variables. Now, Now, I look at the another way, that is del u by del t. Let us look at the equation of continuity. From continuity equation, we have del u by del x plus del v by del y is equal to 0, and that gives me my v is minus integral over minus h to eta, because I have a water surface is y is equal to eta, and my bottom is I have considered as finite water depth. This is y is equal to minus h, and this is y is equal to eta. So, this is my y variation. So, v is minus h to eta del u by del x into dy. Since we have seen del u is a function of x and u is independent of y, so that will give us minus del u by del x to eta plus h. And in the process, what happens when I say I look at, as I say, small amplitude, I look at the linearized cloud waves, assuming amplitude is small. Since amplitude is small, so my v becomes minus h into del u by del x. And again, from the linearized kinematic condition, from the linearized kinematic condition, we have eta t is nothing but phi by, and that is v, that is on y is equal to 0. That is the linearized kinematic condition. Now, if I substitute for this eta t is, so what I will get it, and this is so my v, so my velocity v is minus h into del u by del x, and which is equal to and this is nothing but that means phi y is minus h del u by del x, and phi y is eta t, so that gives me eta t. So, this is what I get. So, from this I can easily get h del square u by del x equal to minus eta t, and in fact, this is the linearized equation of linearized continuity equation for long wave. Now, what I will do the two things. I have the continuity equation and I have the equation of motion. So, the equation of motion is del u by del t is minus g del eta by del x. So, if I look at these two equations, so what will happen? If I eliminate, if I take this del square u by del t square del x del t minus g del square eta by del x square, and again from the first one I will have h del square so this will give me del square u by del x del t. Okay. So, this is minus g del square eta minus, so here minus del t del t. So, if I take h into del u by del x, h into del square u by del x del t minus this, and this is minus h into del square u by del x del t, or this is equal to r plus h into eta t, eta t will be minus del square eta by del t square. So, del square u h del square u, so which implies h del square u by del x del t minus g h del square eta by del x square, and h del square u by del x del t is same as minus del square eta by del t square. So, if I just look at these two terms, that gives me del square eta by del x square is equal to 1 by g h del square eta by del t square. In fact, this is the one dimensional linearized, so which can be written as del square eta by del x square is equal to 1 by c square eta by del t square, and here c is root g h. In fact, this is what the linearized long wave equation in one dimension. So, we started with a flow with a fluid which is two dimensional in nature, and we have arrived at the long wave equation which is one dimensional in nature. And we have seen that, in fact, in the earlier case we have seen that this del square eta by del x square is 1 by c square del square eta. This is basically the one name. Now, what will happen if I consider the two dimensional case? In case of two dimension, okay, before going to the two dimensional case, let me see another thing. So, I have already seen that if I again analyze this element, because I have h del u by del x is equal to minus eta t, and I have del u by del t minus g dot del eta by del x. So, again what I will do, I will just say that suppose what will happen h del square u by, which implies and this implies so what I will do, okay, so which implies if I combine these two, I will say del square u by del t square is equal to minus g into del square eta by del x del t, and this is equal to same as minus g del square eta by is same as g h del square u by del x square, and in simplifying this we will get it del square u by del x square 1 by c square So, again we are seeing here that in this case also, where u is a function of u x t, u also satisfies the wave equation, and here c is equal to root g h. So, now with this understanding, if we will move a little more, suppose I say that I have given a wave, if eta is, if I start with that eta is a function of f of x and t, x minus c t. If eta is f of x minus c t, because we know the general form of eta is f of x plus c t, x minus c t plus g of x plus c t. Now, if I just assume that eta is f of is the general form. So, if eta is f of x minus c t, then what will happen, that I can always find that my u, because we have eta t, is minus h into w by del x, and which implies minus h into w by del x is equal to eta t f of x minus et. Sorry, this is eta is f of eta t minus h into del eta by del x. So, it will give me minus c times f dash x minus et, and then if we integrate with respect to t, then we get u, integrate with respect to x, then we get u is equal to so my u will be, it can be easily seen that my u will be g by c, can be seen that u is g by c f of x minus et, because del u by del s, this will gives del u by del x will be c by h, and then we can see that is so. So, and that is what is equal to g by c, and it is same as, because c is root g h, and that will give us c by h into eta. So, which gives me u is equal to c by h into eta. This can be easily obtained, because obviously from here you are taking one derivative here, and that will be give us this. Then another result I will again we have seen that c is root g h. Once we have c is root g h, then we have u becomes c h, this will be g, c is root g h, so g by h into eta. So, this is another relation. So, it shows that what it says, that the speed of propagation is inversely, speed of propagation is also inversely proportional to the water depth. So, that is what another observation. In a similar manner, we can also get some of the results in case of finite, in case of when you consider f is equal to g is equal to u is equal to, or eta is equal to f of x plus et, and that solution will go on. Now, the question comes, what will happen in case of a 2-dimension, 2D long wave? In case of 2-dimensional case, you can always see in case of a 2-dimensional long wave, you can see that the equation of continuity will be simple. I am not going to the detail, but I follow the similar procedure. Here all the 2 horizontal component of the velocity, there will be 2 horizontal component of the velocity and 1 vertical component. So, if u v are the horizontal component of velocity and v is the u v w are the component of velocity, and let the horizontal component of velocity be u and v, w is the vertical component of velocity, I assume w is negligible compared to u and v. So, equation of continuity in the assumption of the linearized long wave, this equation of continuity will give us del by del x, del eta by del t plus del by del x u into h plus eta plus del by del y b into h plus eta, and that is 0. On the other hand, if you look at the equation of motion, sorry, and if you look at the equation of motion, then we will have, again we can get from the equation of motion, that is similarly we can derive the equation of motion. Can be obtained, and in this, and it can be shown that the linearized long wave equation of linear long wave equation in 2-dimensional or 3-dimensional fluid domain will be del square eta by del x square plus del square eta by del y square 1 by c square del square eta by del t square, and here again c is root g h. This should be, so that will have to find the linearized, and this detail I am not going here. I have just given the equation of continuity, as I mentioned that here we will get two equations for the equation of motion, and then one is in u and v, two relations, and that we eliminate u v and eta, then we once we eliminate u v we will get the linearized long wave equation of in 3D, and here the wave equation is 2D, is 2-dimensional. So, when we have we have seen that when the fluid domain is 3-dimensional, the wave propagation is 2-dimensional, whereas when the fluid domain is 2-dimensional, then in that case the wave propagation is 1-dimensional. Now, again I will just think of another case where we call a case of variable topography. Suppose I say that I have a h which is variable in x, and I say eta is equal to eta x t. Then in 2D we have the equation of motion, equation of continuity, variable depth, long wave equation, variable depth. So, equation of continuity will remain the same, del u by del x plus del v by del y is 0, and it can be simplified. Sorry. We have seen that in case of 1-dimensional this is this. Now, if I am looking at a ocean of depth h, and I just look at the width of the ocean as, if I look at the width as Bx, this is my depth, this is my width, and then this is that depth. Then what will happen to the equation of continuity? Then in that case the equation of continuity will look like del by del t rho eta b plus del by del x. This comes from the conservation of mass u s is equal to 0. And where s is nothing but b x into h x, and assuming rho is constant, then we will have del by del t into beta plus del by del x u s 0. This is the conservation of mass in case of a variable depth and a variable width. Now again we have the equation of motion. We have the equation of motion, that is del u by del t plus minus g del eta by del x. This is equation of motion in case of 1D, and if you combine this, so then what will happen in this equation? S is h x b x, b is. So, if I say h is equal to h x is equal to h and b x is equal to b, this is the most general case, then equation of motion will remain the same, whereas the equation of continuity will reduce to this equation of continuity becomes del eta by del t plus del eta by del t, this is equal to plus b will go plus h times del u by del x 0. And this is what we have seen, that in case of a one dimensional, this is the case of a one dimensional long wave, the equation of continuity, and if we combine this, this is, so this is the equation of continuity. For variable depth and breadth, but when h x is h and b x is b, that means again the same equation of continuity, and if you combine this, that means if we have a channel of width b and depth h, which is a constant, then you can see that same del square eta by del x square is equal to del square 1 by c square del square eta by del t square. So, this is again same equation is satisfied if we are thinking of a channel of constant width and constant depth. So, it is so from one dimensional to, we are always looking at a problem where the channel width is constant, then also same one dimensional wave equation is satisfied. Now, I will further generalize this. The next generalization I will have a look at it. Another case I will take. In this case, and in this case I will say that suppose h x is a, suppose I consider we have already seen that in case of a channel of when b is equal to b x, if b is equal to b x, then we have del eta by del t, then we have b into del u by del t, rather b del by del t b eta. So, equation of continuity del by del t b eta plus del by del x into u, s is u s is equal to 0, that is the continuity equation, and when b is equal to b x, and we have the equation of motion, that is del u by del x. That is this is the equation of continuity. Then equation of motion is del by del x, that is del u by del t is equal to minus g del eta by del x, and which can be written as, if I say b, this is b. So, that means I also can write it as del by del x u b del u by del t, b del u by del t is minus g b del eta by del x, and I have the, this is from the equation of, and here del by del t I have b eta minus del by del x u h s. This is from here, there is some juggleries we have to do, and then we have seen that then what will happen, del by del x b eta. So, UHS, that means UHB. So, I will say that del by del x, if I take del by del x of del square u b, b is eta is a function of x and t b. So, that will give me b del square u by del t square. So, if I take from here, I will get b del square u by del t square, and that will give me minus del by del t minus b g del eta by del x, and again, so that is minus b del by del t. So, this is b g del eta by del x. So, that means del by del x of del by del x of minus h g b h g b So, h is a constant. So, if I take this del by del x of h g b, okay, let us see this. I have b del square u by del t square. So, I can easily get a del by del x g h minus g h into b h g b into del eta by del x, then this gives minus b del square eta by del t square, and again this will give me finally g by b. I can easily get it with little juggleries, del by del x b h del eta by del x is equal to del square eta by del t square. So, this is what happened. This is what happened when h is not constant and b is not constant. Now, this is for variable depth and width. So, this is one equation, and now again these steps one has to follow little, and then one will arrive easily this. I just leave few steps here. Then one can easily get, in particular when h is equal to ax, b is equal to ax and h is equal to constant, then this will give me, that is h is constant. So, this will be g h by, because by b is a x into d by dx, b h into b is a x, h is constant, already h has gone. So, this is a x into d eta by dx equal to del square eta, and if I have equal to del square eta by del t square. So, if I write eta x is equal to eta x t equal to eta x into cos omega t, then this equation will give me g h by a x into d by dx, a x d eta by dx plus omega square eta is equal to 0, and that gives same as a get cancelled, that gives me 1 by x, g h is c square, and my g h is c square. So, it is 1 by x d by dx into x d eta by dx plus omega square by g h is c square by g h, let me put it 0, and then omega square is, we have g h is c square is g h, and we have c square is nothing but omega square by k square, and c square is omega square by k square, that is g h. So, that means omega square by g h is same as k square. So, it gives me 1 by x d by dx, x into d eta by dx plus k square eta is 0. If I further simplify this, that will give me that d square eta by dx square plus 1 by x d eta by dx plus k square eta equal to 0. So, this is the case, this is the equation of long wave, and for a channel where the width is varying, where the depth is constant and width is varying like this, is a channel in which, and it can be seen that this is a kind of a first order 0th order Bessel equation. You have this is the 0th order Bessel equation, and you know the solution of this equation is very interesting, that gives me eta x t, the solution of this is c naught j naught, rather call it c 1 j naught k x plus c 2 c 1 c 2 y naught k x into cos omega t. This is the general form of eta, and again as we know that the property of y naught as x at near x is equal to, at x is equal to 0, y naught will tend to infinity, and however, we are looking for eta whose solution is bounded at the near x is equal to 0. So, that shows that will say that c 2 has to be 0. So, in the process we get eta is equal to c 0 c 1 j naught k x into cos omega t, and again if I say, suppose I say eta is equal to s by 2 cos omega t at x is equal to L, and that gives me c 1 as s by 2 cos omega t, c 1 will give me c 1 is if eta is at x is equal to, then my c 1 will be h by 2 cos omega t, h by 2 into j naught k l, because cos omega t at x is equal to L, this will be C 1 j naught k L, and C 1 j naught k L is h by 2. So, C 1 is h by 2 j naught k L, and which implies my eta, if eta is this at x is equal to L, then that will. So, my C 1 is this one, C 1 is this, my eta will be h by 2 j naught k x by j naught k L into cos omega t. This is what the, so I am looking at this will be the general form of the solution. And this is a like there is a wave which will here my channel will look like this. This is at x is equal to L, and at x is equal to 0, this is the channel is like this. And this is the way it will look like, and it can see that this is a spherical, it is a cylindrical waves, particularly cosine type wave which decays at. Now, in the same way, I will not go today much into the details of more about the waves, but I will again summarize few more simple cases. So, let me just say few things. We have all seen that equation of continuity in 2 dimension, and that is what it is, del eta by del t plus del by del x u into s plus eta plus del by del y v into h plus eta equal to 0. I have already seen this. Okay. Now, I just leave this as homework to do again prove it, as I told earlier that we will discuss, it can be obtained, but here I am now giving it as a homework. This is the equation of continuity. What about the equation of motion? In 2D, 2 dimensional equation of motion, and that will give me, that is we will have already what we have already here, that we have del u by del t plus u del u by del x plus v del u by del y minus g del eta by del x, and we have del v by del t plus u del v by del x plus v del v by del y. This is equal to minus g into del eta by del y, and again if you linearize this. So, if we linearize this, that what it will give. So, on linearization, I just from this it can be easily shown that there are 2 things which satisfied, I rather say, and here we have assumed y is equal to eta, which is a function of, sorry, rather z is equal to eta, which is a function of x, y and t. So, these are the some of the hints for the 2 dimensional, sorry, x, y, t. Then in that case equation of motion will be these 2 equations, whereas the equation of continuity will be these 2, and this again whereas in this case we assume w is vertical, w is negligible, because we are assuming w is the vertical component of velocity and this is negligible, where uv are the horizontal component of velocity, in which and from this we can say that if you apply the small amplitude, linearize it. Once we linearize, then from the equation of continuity and equation of motion, we will get del square eta by del x square plus del square eta by del t square del rather y square in fact this is the most another simple result I would like to mention here. So, although initially I told that this can be easily proved, but I think that little hints will help you to arrive at this, and this is very easy because again just like the case of one dimensional case we can do this. So, in fact this 1D and 2D waves, and as I have mentioned that in case of for a 2-dimensional fluid domain we have a 1-dimensional wave equation, whereas for a 3-dimensional fluid domain we have a 2-dimensional wave equation, and where in this case of course eta is a function of x, y and t. So, these two equations, these two long wave equations, 1-dimensional and 2-dimensional long wave equation plays a significant role in several analyzing several problems, several problems associated with the wave propagation along a coast, particularly when you look at the cases like tsunami, planetary waves, particularly where the wavelength is this is shallow water waves for the long waves, or even if for the analysis of storm kind of situation, even if in many cases this linearized long wave equation is considered, and this gives quite better rather I will say the sophistication is quite satisfactory. It is although we have taken the small amplitude waves, but particularly when we have seen that the travel time chart, tsunami travel time chart that is prepared at various country, often the linearized equation of the long wave is taken into account, because the formula they have taken in many cases as c is root g h, and of course. So, this large class of problem of ocean engineering can be handled under this assumption of long wave theory, where the wave amplitude is assumed to be very small, and we will consider few more cases of bottom variation, how the variation of bottom topography or the surface disturbances, bottom topography, a jet disturbance in the bottom or disturbance on the surface, bottom topography or surface disturbance, topographic disturbance or surface disturbances. It helps how these are accommodated into the long wave equation or the equation of while solving the equation, because in all these two cases, in both the cases we have assumed P is P atmosphere and which is taken as 0 without loss of generality. The question is that when P is not, suppose there is a wind, there is a storm, in such situation how the, because in such situation atmospheric pressure is not constant. Further, in many cases we have taken y is equal to h, that is h is a constant, h is a constant. So, but in reality that is not so, as we have seen in the previous case, how the width variation has changed the nature of the problem, and how the wave propagation has changed. So, these things few, at least few cases we will consider in detail in the next few classes before going to close this wave propagation, wave motion chapter, or basically the discussion on wave motion. With this I will stop today. Thank you.